So today we'll wrap up our discussion on dispersion by discussing some dispersion compensating techniques. Okay, so when the various dispersion compensation techniques can be classified sort of into optical techniques and electrical techniques, right? Optical techniques are where in the optical domain itself we try to compensate, whereas in the electrical domain is after photo detection at the receiver, we try to do some electrical signal processing to sort of get rid of the distortions due to dispersion. Right, so we look at the optical techniques first. So of course, one can just use what are known as dispersion compensating fibers. In our discussion of dispersion, we saw that like basically the total dispersion in a fiber is a contribution of material dispersion plus waveguide dispersion. Right? Material dispersion is sort of intrinsic to silica, the glass material, but the waveguide dispersion depends on sort of like the core size, index contrast between core and cladding, and such, right? And so we saw that how we can make fibers with different dispersion profiles by controlling those parameters. Right, so basically we can, so if you imagine a link, so you have some transmitter, then so you have the standard sort of single mode fiber that is used for optical communication links, right? So this is your link of length L, and then of course depending on the wavelength of operation, etc., there will be some broadening here, right? So this of course has some particular dispersion value, like some GVD constant beta 2 or some dispersion value D, right, equivalently. So what one can do is, like, before the receiver have some length of dispersion compensating fiber which has the opposite sign of dispersion, right? So let's say this has a beta 2 value of beta 2 DCF and a length N DCF, right? So we put this fiber to compensate for the broadening happening in your standard single mode fiber, and then send it to your receiver. Right. So as we discussed, so the pulses sent out here, right, will have some spectrum, right? And basically, what dispersion does is that we saw that what it basically does is just adds a frequency dependent phase shift, right? So here basically right, you have that. So if you just consider the GVD or second order dispersion, then basically you just have something proportional to omega square times the length, right? So similarly, like if once the pulse is propagating through this DCF, right? Similarly, the DCF would add its own phase shift depending on the length and the GVD value of the DCF, right? So here, basically, if I look at the spectrum at the receiver, right? So that will be this multiplied by the DCF response, right? And basically, if you want to get rid of the broadening or distortion due dispersion, basically we want this to come out to be equal to the input vector, right? So if this comes out to be equal to the input vector, that means basically there is no net dispersion. What I send at the transmitter is what I am receiving. So basically you want this factor to be 1, right? So basically you can see from here what you want is, so beta 2 times L, which is for the fiber that is used for the link, should be negative of the value for the DC. Right. So basically you want the dispersion to be opposite sign. Right? I mean, you could equivalently write in the D parameter same thing. So the D of this SMF fiber should be negative of the D parameter. Right. So, so for example, if you take the standard SMF and the standard telecom wavelength, the most widely used telecom wavelength of 1.55 micron, then we saw that for the standard single mode fiber, the dispersion value is about 16 picosecond per nanometer kilometer, right? So, so basically we can make DCFs which have negative dispersion. So this dispersion value is positive, so it's anomalous dispersion, right? For the standard fiber. But again, using this waveguide dispersion and making the waveguide contribution large, we saw the waveguide contribution was negative, right? So making a very small core and increasing the index contrast between the core and cladding, we can make DCFs which have quite negative, like up to 100 picosecond, minus 100 picosecond per nanometer kilometer. Okay. So you can see that by using a length of this DCF, which is sort of the ratio of this, so 1/6 roughly of my link length. If I add a DCF of roughly 1/6 the link length, here I can compensate for this. Yeah, so for example, if you have a 100 kilometer fiber here, then you would roughly need about 16 kilometers of DCF before the receiver. Right, so it doesn't come for free, of course. These DCFs, because they have stringent requirements on the core side and the core cladding index difference, etc. Typically, they come with higher loss, right? So the standard single mode fiber, we know it's 0.2 dB per kilometer loss at this wavelength. DCFs typically have 4 to 5 times that loss. Okay, so when you are adding this fiber, you have to take that extra loss into account. Also, the bending losses, etc., for these DCFs are also typically higher. Okay, so that's something that needs to be taken care while designing your link. And so one can also try to do better, right? So let's say you've compensated for the group velocity dispersion. Then we saw that beta 3 will start limiting, right? So then basically we saw that if you include the beta 2 term, beta 3 term, then there is a phase shift due to beta 3 here, which goes as beta 3 times omega cube, right? So one can also try to design a fiber now which tries to compensate for beta 3 also, right? So let's say this DCF also you try to optimize the third order dispersion. Right. So if you can obtain the same condition for beta 3 also, right? That is beta 3 times L for the standard fiber that you're using for your link is negative of beta 3 times the length for the dispersion compensating fiber, then it can also compensate for beta 3. Right? So if you can get these conditions simultaneously, right, that would happen if the beta 3 of your dispersion compensating fiber has this value. So right. So basically the ratio of beta 3 to beta 2 for the dispersion compensating fiber has to be the same value as the single mode fiber used for the link, except the sign has to be opposite. Or yeah. Right. So people also design. Of course, now the design becomes more complicated, right? To get both these conditions, right? Opposite beta 2 sign and opposite beta 3 sign, but also value equal to that. But there are some very special fibers which can do this. So then you would be able to compensate for both beta 2 and beta 3. Right, and this kind of special fibers where you can compensate both for beta 2 and beta 3, right? Equivalently, I can write this in terms of the dispersion slope S, right? So remember, this was the derivative of the dispersion parameter with respect to wavelength, right? So this S times L. So the S value should be opposite, or the dispersion slope should have opposite sign, right? So if you can get a fiber like this, then that's also useful in sort of broadband WDM systems, right? So recall that typically, so this beta 2 or D is also a function of wavelength, right? So in general, you can see that basically maybe I can satisfy this at one particular wavelength, but if I move to a different wavelength, then basically for both these fibers, the dispersion will change by different amounts, and you cannot satisfy this at the new wavelength, right? So typically, you would be able to satisfy this only for like a particular wavelength or a very narrow band of wavelengths. But if you want to use some broadband WDM system with very different wavelength channels, right? How do you compensate for dispersion along all the channels? You can actually do that if you have such a fiber, which satisfies this beta 2 and beta 3 condition, right? Why? So, right. So if you plot dispersion versus wavelength, right? So typically, let's say it has something like this, right? We saw for the standard single mode fiber, right? So like at 1 point, so it will cross 0 around 1.3, at 1.55 micron, this is about like 16 or something, right? So this is being right. So there is a slope, right? The dispersion is wavelength dependent, and there's a dispersion slope, which is this S, right? Now, so if we use a dispersion compensating fiber, right, which has this condition, so it has an opposite sign for D, right? So let's say at 1.55 we do that. So 16, let's say, for example, this one has minus 100. Right? But also it satisfies this condition, right? So the slope is negative of the standard fiber, so the slope is like this. Right? So now you can see that if this condition is also satisfied, then if you take any other wavelength here nearby, right? So the amount of change in D here will be compensated by the amount of change in D. Right? So basically, at this new wavelength also, you will be able to satisfy this. Right? Because D at this new wavelength is just D at this wavelength plus the dispersion slope times the difference in the wavelength, right? So if you also match the slopes, then basically over the range where you satisfy this condition, right? Over this entire band of wavelengths, you can compensate for the dispersion. Okay. So these kinds of fibers are useful for broadband WDM systems that you have many different wavelength channels, and you want to compensate for dispersion in all of them. Okay, so yeah, so that's one optical way, but it's usually expensive, right? These dispersion compensating fibers are expensive, and you typically need many kilometers, right? We saw roughly you need like 1/6 the length, so we have hundreds of kilometers of fiber, so you still need like hundreds of kilometers of TCF, and plus you have to compensate for the additional loss, etc. here, right? So it's used in some places, but not everywhere. So let's look at another optical technique. Any questions on this? Right. So another optical solution which is more compact than having this dispersion compensating fiber is to use what are known as chirped fiber Bragg gratings. So PG stands for fiber Bragg grating. So I mean, you know from the fiber optics course, right? Basically, a fiber Bragg grating is where you take a fiber and then you write a grating. So you shine UV light and you change the refractive index slightly in regions of where the UV has high intensity. So you make a grating where periodic high and low intensity, like that, a high and low index. So this is the core region and this is the cladding region, and then you change the index by some small amount delta n. So we saw that the index difference between N1 and N2 typically for these single mode fibers is like, let's say 10 to the minus 3 to 10 to the minus 2 in that range. This delta n is typically 10 to the minus 5, 10 to the minus 4, so quite small. But anyway, so we saw that because of this grating, what you can have when you satisfy the black condition, right? So basically when the incident light has wavelength which satisfies the Bragg condition, right? So if this periodicity is capital lambda, so when lambda b is that value, right? Then you know that because of this Bragg grating, it gets reflected. Right? So you get a peak in the reflectivity spectrum. Right, at this Bragg wavelength. So you can design like, for example, filters at particular wavelengths with some particular band using these ratings. So how do you use this for dispersion compensation? So what we do is instead of having a constant period here, we actually chirp the period, right? So chirp, you know, like when we were discussing pulses, chirp pulses. So there, the frequency was varying with time, right? So here we vary the period with distance, right? So either like a increasing distance, right? So now this is a function of z. Z is the propagation direction, right? So this is now a curved gradient, right? So either you have the period increasing with length, or you can have it decreasing with length. I mean, it's equivalent. You would have one particular grating, and the functionalities would be opposite if you incident light from here or here. So from this direction, the period is decreasing, but from this direction, it's increasing. But anyway, so now you can imagine that. So in the initial period, right? Sort of. So I'm exaggerating, of course, here, right? The change is not this big, but so here in the initial period, the period is small, right? So from this condition, you can see that the wavelength which will reflect it back from the front of the grating will be smaller. Right, so let me call this some lambda min, right? And then as you increase the wavelength, it will penetrate deeper into the grating because this condition will now be satisfied for a larger period, right? And up to some maximum wavelength here, which goes all the way to the end of the grating and then reflects back. Okay, so now if you look at the reflectivity spectrum versus wavelength, it will be much broader than the constant period grating, right? Because now there's a range of wavelengths which will be reflected from lambda min to lambda max, right? So that again depends on how much I've changed the period of the grating. Right, so not only this, but what's happening here is that you can see that this wavelength is traveling a longer distance, right? So if this is length of the total grating and g, then you can see that basically the lambda max wavelength is traveling almost twice the grating period length more than this minimum wavelength, right? So if there is some bandwidth here delta lambda. So the delay between these two wavelengths, right, is basically the extra path length traversed by this wavelength divided by the speed. Okay, so that's the delay between these two, right? And you can see that this is something like dispersion, right? Because what was dispersion? The fundamental cause was that the propagation constant and hence the group velocity was a function of wavelength, right? So different wavelengths were traveling at different speeds, which ultimately resulted in a time delay between the different wavelengths at the receiver end, right? So basically here also you can see we're getting a time delay between different wavelengths, right? So again, now if we can get this time delay to be the opposite sign of what we got from the fiber dispersion, then we can compensate, right? So if this is the time delay, again by making an analogy to the dispersion, I can write this time delay as basically a dispersion coefficient for the grating times length times the bandwidth, right? So this is basically what we had for the broadening in time. Right, so basically the dispersion coefficient was the broadening time per unit length per unit bandwidth. So we can write this for the grating also here. And from here, if you substitute this value for delta t here, basically we get an expression for the dispersion coefficient, effective dispersion coefficient of the grating. So that just depends on the refractive index of glass divided by the bandwidth of the grating. Okay, so if you put a typical number, so let's say if I design a grating of about 1 nanometer bandwidth, okay, you can see the value here is very large. It's about 10 to the 7 picosecond nanometer per nanometer kilometer. Okay, and again, recall that the fiber dispersion values are typically like tens of picoseconds. So this is many orders of magnitude more, right? And now again, to compensate for dispersion, like so if you have some length of fiber here, the dispersion coefficient D, length L, so we put a chirped fiber rating here before the receiver, and if this has parameters dg and length of the grating lg, right? So again, the same condition that if d times l is negative of dg times lg, then I'll be able to compensate for the dispersion. But now because dg is so large, you can see that all I need is a few centimeters of this fiber gravity. Okay, so
excuse me, sir.
Basically, like about 10 centimeters of this chirped FPG can compensate for about 100 kilometers. Okay, so yeah, but yeah, typically you can do this for you design this for a particular wavelength, right? So again, so you will design it at some particular wavelength. If you move to a different wavelength, then this condition in general will not be satisfied. So typically these are used for individual wavelength channels. You can't compensate for a very broad bandwidth for WDM systems. If you want to use this for WDM system, then typically you have to first use like a demultiplexer, wavelength demultiplexer here, and separate into different channels into different fibers, and then you can use an FPG for each wavelength. So the question is this expression approximate or exact? I mean, you can try to make it as approximate, as more exact as possible. So of course, this has to be the group index for it to be right, because we're looking at the time delay between pulses. And of course, it's not totally exact in the sense that this does not get immediately reflected from the, even this has some penetration depth. And basically, you know how the grating actually works is that you get some small reflections from each sort of slice of the grating, right? Which sort of constructively interferes and makes a big reflection. So, yeah, in that sense, it's not maybe totally exact, but it's due to these effects. I don't know, the correction should not be too much, maybe a few percent or something. So this is still good enough to use because again the values you're talking about are so large, right? So that
In Bragg's wavelength formula, N is N effective or
sorry, was there another question?
sir in Bragg's wavelength formula, what is N effective?
Yeah. Right. So you have some mode here, which is incident. And again, so N1 and N2 are very close, right? For single mode fibers, and N effective lies between N1 and N2. So for all N here, you can either use the core index or cladding index. Doesn't make much difference.
Sir,
Yeah.
why we are periodically increasing the spacing between the grades?
because we want to introduce a delay, right, between the different wavelengths. So we want, I mean, dispersion is basically different wavelengths traveling at different velocities, which leads to a delay, right? And we want to compensate for that. If you have a constant, I mean, even then you'll have some. So here with a constant grating, basically you have some spectrum like that, okay? And basically you've designed to reflect one particular wavelength. But even here, of course, there is some phase response, right? So this is the sort of the amplitude or the intensity response. There's also some phase response, which is roughly sort of like the derivative of this, right? So there's the different wavelengths slightly away from resonance will acquire different phase shifts, right? Which will also lead to some like a phase shift can be looked at as a time delay, right? So using this effect technically, you could also sort of get some delays, but the problem here is these delays are very non-uniform, right? So this is like a sharp spectrum here, and the phase shifts are varying very fast with wavelength. So the time delays equivalently are also varying very fast. In this case, sort of the phase shift is sort of more flat and linear, so the delay is sort of constant, and you get a constant dispersion value. But here it's varying very fast, so effectively, like, it's as if this grating has higher order dispersion terms, which are also very large. So yeah, so in fact, like right at resonance, the delay is actually very small. Okay, so for this constant period grating, so you can see that this is just not very easy to use or not very convenient, right? But here, like, you can easily design the grating for the dispersion you want, and typically only chirped ones are used. So for the chirped ones, basically the point is this only the dispersion, this second order dispersion dominates, and that's the maximum. The higher order dispersion are all very small, can be neglected, and also this is constant over sort of this wavelength range. Whereas here, for a constant period grating, this phase shift and the delay is varying quite sharply over a very small bandwidth, and so you have third and fourth order dispersion terms, which will be comparable or maybe even higher than the second order. So that would give you additional pulse distortion, right? Yeah, so I hope that's clear. Okay, so both these optical techniques that we discussed, like dispersion compensating fiber and chirped fiber backgratings, they were both, you can use them irrespective of what your transmitter is, right? So it could be an incoherent source or a coherent source. We saw that sort of the broadening mechanism in these cases are slightly different, right? In the incoherent case, basically just the source bandwidth determines the broadening. In the coherent source case, basically you get this chirping effect, and basically the pulse width of the data rate itself is determining the broadening. But anyway, in both these, for both those cases, you can use these techniques basically because you're compensating for the fiber dispersion itself, right? So it's like you are adding something which is like a negative of the fiber. So whatever you send in, effectively the whole system is as if it sees. Okay, so these are two main optical techniques which I use, and then there are electrical techniques. right? So where basically we try to compensate in the electronic domain. Right, so electrical or electronic techniques. So the most popular one is to use digital signal processing, or basically some electronic filters, right, to uh, compensate for this distortion that is happening in your pulse. Right, so recall for incoherent transmitters, where the source bandwidth is much larger than the data rate. There, basically, we could model the fiber as some transfer function here, right? Like effectively some low pass filter kind of thing. Right. So this filter response depended on the beta 2 and the beta 3 of the fiber, right? So basically, using that response function, right, we can basically calculate. So for a given pulse, what is my pulse at the receiver here, right? And then I can try to compensate after I photo detect here. And so here this is optical here in the fiber. Once you photo detect, now you're back to the electrical domain, right? And now I can use try to use some electronic filtering or signal processing techniques, right? So, for example, the simplest thing you can imagine is like if I have a filter here which is the inverse of the fiber response, right? Then I get back what my transmitted thing was here, right? So once I photo detect and sample it, I have a digital signal here, and then I can basically use standard DSP chips and algorithms, etc. So I can implement like any kind of filter function, etc. Okay. So that's bucket, right? And recover this pulse. Right. So of course this kind of transfer function we could only write for incoherent sources, right? Where there is sort of this chirping phenomenon, this kind of thing is not happening. It's basically just a collection of different frequency wavelengths which are carrying some different fraction of the power and which sort of get delayed. So you can sort of compensate for those delays and get this back. So there's no interference happening in the electric fields of these different components. Right. So we saw how to model this, and one can compute the inverse, and using digital signal processing, digital filters, one can easily implement those kind of things. So for coherent sources, which are typically used in modern day systems, of course now we can't model the fiber as some transfer function, but we know what the effect is, right? So here there's a coherent source like a laser at a particular frequency omega naught, right? And then we are making some pulses here. So there's a carrier frequency at frequency omega naught. right? And then propagating through this fiber, basically we know that the pulse gets chirped, right? Or equivalently, basically what is happening again is that in the frequency domain, we are multiplying by a phase shift, right? So this has some amplitude spectrum A of omega, consistent, or yeah, it means use omega here. So then I'm centered around omega naught, right? So spectrum looks something like that, right? So the bandwidth here is inversely proportional to the pulse width in time domain, right? And then here after fiber propagation, basically what's happening is this is getting multiplied by a frequency dependent phase, right? So right, so here basically this thing was something, so if you take beta 2, then right, you could take additional terms also, but so now you're multiplying by frequency dependent phase. So this thing you're multiplying by a phase which is quadratic around the center frequency, right? So basically again the point is to compensate for this phase shift, right? Like in the optical techniques we saw, basically now we propagate this pulse through some additional optical medium which incorporates an opposite phase shift. Right, so in the electrical domain, if I directly photo detect this, right, then I lose this phase information, right? So then it's difficult to compensate because once you've lost the phase information, then there's no way to recover the pulse, right? So, but what you can do is what is known as coherent detection. So basically here at the receiver, you beat your incoming signal with another single frequency laser here, which is at a slightly different frequency. Okay, so there's a local oscillator, which is basically another single frequency laser here, whose frequency is slightly shifted. Okay, from the transmitter frequency. So basically, you beat this local oscillator with the incoming signal and then send it on to your receiver. And now, again, you know that when you beat two signals, basically what you will see at the detector will be the beat frequency, right? So the beat frequency between these two will be at this difference frequency, omega IF, right? So basically, this spectrum I will translate it down to omega IF, right? So I'm multiplying this by another frequency here, right? So this is the omega IF, right? So the beat between these two will give me this spectrum translated with center frequency omega IF, right? So the electronic signal coming from my photo detector now, right, will have a center frequency omega IF, right? And the spectrum will basically be what the spectrum was here, right? Including the phase. The phase is also preserved, right? So, in other words, if I look at the total electrical waveform here, that will have some oscillations, maybe like this, with the chirp also there. Okay, so now what are the spectrum here, right, is basically this spectrum. So right, so this is the input spectrum, which is A0, omega. So this is A L, omega, right? It's basically this spectrum shifted to omega I, right? So, it's just the same spectrum, but just centered at omega, right? So I can write this as basically A0 omega multiplied by this phase, but now centered here, right? So I put so this additional factor here, you can see, so this will be now something like that. Right? So it's just centered at omega I. So again, there's a question why this local oscillator is used. Again, if I directly photo detect it like this, right? So then what I will measure is the mod square of this, right? Or in other words, if I look at the time domain, right? So let's say I have some chirp pulse here after the fiber. I will just measure the envelope, right? So I just measure the mod AT square. And so recall that the actual pulse is something like e to the minus t square by TL square, and then there's a chirp here, right? So basically I lose this phase information, right? So I'm just measuring the envelope here. And so now how do I, so now I just have an electrical signal. If I directly photo detect, I just have an electrical signal with pulse like that. So how do I compensate it to get back this narrow pulse? Right? There is no way, because the difference between these two was in the phase of the carrier, right? That is what is leading to the broadening. So if I lose that phase information, right? If I'm just detecting the envelope, then there is no way to now recover this shorter pulse from this broader pulse. So somehow we have to preserve the phase information. So that's why we are using this local oscillator, right? So we are beating two signals and then translating this optical signal into the electrical domain, right? So this omega IF is typically, let's say, tens of gigahertz, between let's say 10 to 50 gigahertz. Okay, and that's within the photodetector receiver bandwidth. Okay. So let's say the bandwidth of the receiver is 50 gigahertz. This omega IF and so the bandwidth, so the data rate, the bandwidth here would be the data rate, right? Or the inverse of the pulse width. So that's again typically tens of gigabit per second, so tens of gigahertz, right? So this will roughly, let's say, go from 0 to somewhere like 50 or 100 gigahertz, right? So basically your photodetector bandwidth has to be more than that. So typically the photodetector bandwidths are in this range, let's say 50 to 100 gigahertz, which are used for high capacity systems, right? So now this is basically beating with the local oscillator signal, you still have the phase information preserved, right? So basically another way to see it is so in the photodetector, what is happening, right? You have some incident field, and basically the photodetector gives out a current which is proportional to mod E square, or the power. So because it's mod E square, you lose all the phase information. But here what you are doing, you have two fields here, E1 and E2, right? And then once you send E1 plus E2 to the detector, maybe I should do this here. Right, so So now the total field here at the for the detector is E1 plus E2, so it detects mod of E1 plus E2 square. Right, so you'll see, of course, there'll be a mod E1 square, mod E2 square, but there'll be a term, cross term, like E1, E2. Right, so this E1, E2 is basically giving you this. Right, so now this still has so E1, this has E1, right, which has the total phase information of my incident. So I need a signal which is proportional to the field, not square of the field, mod square of the field. So that's what this beating with the local oscillator is doing. So you can imagine you need this technique if you, instead of the intensity, if you encode the information in like phase or frequency, right? If you have phase shift keying or frequency shift keying or these more complicated modulation schemes like quarter-shade amplitude modulation, things like that, right? So there also you cannot use just direct photo detection, right? Because you need to recover phase information. So there also you use this beating with the local oscillator. So this technique is called coherent detection for that reason, because it's used to detect coherent modulation schemes, right? Where you also have phase information. So basically the same thing is being done here. So in this case, the information is still sort of just in the intensity, but we want to compensate for this broadening whose information is encoded in the phase. So because we need this phase information, the only way to do that is to beat with this local oscillator. Omega minus yeah, so this will be centered at omega I. So yeah. So yeah, maybe more precisely, I should write like this, and here it should be yes, omega minus omega naught. Okay, so this beating is this cross term, right? So this one of them goes as e to the I omega naught t. The other one goes as, so there's a conjugate, so it goes as e to the minus I omega naught minus omega if t, right? So you can see the product of this, you will have e to the I omega if t, right? So it will be centered at omega I. Okay, so basically with this local oscillator beating, and now if you detect the electric signal now has your complete amplitude and phase information, just the frequency you translated from the optical domain down to the electrical domain, because you are in the electrical domain now and you want to do electrical processing anyway, right? Right. So now again, so you have some time domain and frequency domain signal here in the electrical domain, and now again you can use digital signal processing techniques. You can use digital filters, right? So now what I want to do is get rid of this phase, right? I want to recover just this, the input spectrum. So I want to get rid of this phase. So I'll have a filter here. Whose frequency response will be this minus of this. Right. So I'll have this filter response like this. So yeah, omega is 2 pi f. Right. And I know the beta 2 and L for my fiber here. So I can construct an electronic digital filter like this, and then send this electrical signal through that filter. And then after this filter, I recover my initial spectrum, and by consequence, the time domain loss. What will be the range of values for omega IF? Yeah, I already talked about that. Right? So tens of gigahertz typically, because again, so the data rates that are used are typically tens of gigabit per second, right? For one wavelength channel. So again, so this is about 10 to 100 picosecond in that range, right? So this bandwidth here is about, let's say, 10 to 100 gigahertz. So basically, omega IF has to be larger than that, because you want the spectrum to fit, right? If this becomes lower, that it goes below zero, then it will overlap with the negative frequency, and you will get what is known as aliasing or some distortion here. So typically, omega IF has to be larger than the data rate. So typically, data rates are, as I said, like tens of gigabit per second. So maybe in the 10 gigabit per second, 50 gigabit per second per channel. So omega IF is kept in that range. And your photo detector bandwidth has to be larger than that, so that it detects this signal which is varying at omega IF. Okay, and the nice thing about again this electronic technique is that so you can do this for each channel, right? So you don't need any additional optical components, right? All you need is just this local oscillator, so another laser at your receiver. But apart from that, you don't need any additional fiber or any of that kind of thing. And you can also tailor this to your requirement, right? For example, if I want to compensate for the next order, third order dispersion, then I just have a filter which also has the third order term, right? So it will also have this omega minus omega IF cube, beta 3, right? So in principle, I can compensate for all orders of dispersion just by choosing the appropriate filter, right? So I mean, I would say nowadays this DSP technique is the most widely used because of advancements in electronics also, right? You get very fast DSP chips, and you can make really complicated filters, and you can do this very lot of processing in the electrical domain, which is not so easy to do in the optical domain. So, and you can do this at different wavelengths again, right? So, if you have a WDM system, then you separate. You have a demultiplexer first, and then you separate into different wavelength channels. And for each wavelength channel, then you can, depending on the value of the beta 2 at that channel, you can have its own digital filter to compensate. Right? And these electronic things, as you know, with again electronic integration, etc., like in one IC, something you can have like thousands of these circuits, right? So it's not much of a problem. Okay, so yeah, that's. Yeah, I hope this technique is clear. As I said, this is probably the most widely used technique nowadays. Just because of its versatility, you can. Okay, so another sort of electrical technique that you can use, but this one you do at the transmitter itself. So it's a pre-compensation technique, not post-compensation, right? Is again, so recall that this broadening that was happening. Okay, so one thing is that, so this only works for, I mean, for the incoherent sources, you can just use the fiber as some linear system as a transfer function and then multiply by the inverse, right? This beating in the local oscillator, of course, you only use for coherent sources. If you have a coherent source, then you can also pre-compensate again by taking note of this chirping phenomenon, right? So basically, this broadening is happening because of chirping, right? So let's say you start with an unchirped pulse at the transmitter. Due to the fiber dispersion, the pulse is getting chirped and broadened. So we also saw that if you start out with a chirp which is opposite in sign to the one that the fiber is introducing, then basically the fiber will reduce the effective chirp, right? And basically the pulse will actually compress until some point where the chirp goes to 0, and then beyond that it will start broadening. So effectively, like we saw, right, it was much better than. So we saw like the broadening if C is the same sign as beta 2. So let's say beta 2 is positive. If C was also positive, then basically the broadening was worst. If the input chirp was 0, then it was like this. If the input chirp was negative, then it was like that. Right? So you can see that if my input chirp on the pulse is the opposite sign of my beta 2, then actually I can mitigate the broadening, right? So that is what is used in this technique called pre-chirping. Right, so here what you do is like you have your laser source. Right. So before you put your electrical data, right? So you use some electro-optic modulator to, and specifically you use what is known as an intensity modulator, right? So that basically now the optical pulses intensity is also modulated like your electrical pulse train, right? So this is optical power now. Okay. So instead of directly if you directly send the laser output, so now the laser output is just a sine wave at omega naught. If you directly send it to the intensity modulator and send it forward, then you get what are known as unchirped pulses. There is no chirping. You can also directly modulate the current into the semiconductor laser here, right? So you can have a modulated current like that to directly modulate the output power here. That leads to typically a negative chirp. Okay. So if you directly current modulate the laser, just due to the carrier dynamics within the semiconductor material, you get what is a negative chirp, okay, which is basically the carrier frequency decreasing with time within the pulse, right? So beta 2, again, if you see a standard single mode fiber, right? So beta 2 is actually negative for the telecom wavelength, right? So once we go beyond 1.3 micron, beta 2 is also negative, or D is positive, right? So now C is same sign as beta 2. Okay, so we are in this case, worst case scenario. Right, so that's one reason why we don't use electrically modulated semiconductor lasers nowadays. Another reason is that the bandwidth that you can get with directly current modulating is limited to maybe 1 Gbps or maybe maximum like 5 Gbps. But going beyond that, direct current modulation just from the RC time constants and the carrier dynamics in the laser, you can't go faster. So nowadays we go to 40 gigabit per second, 50 gigabit per second routinely, right? So basically we use external modulator. And so external modulator, intensity modulator does not give any chirp, right? So then you go here in this middle case. But again, for very long haul systems, we want to do even better, right? So we want to go to this case. So what we do is we have a phase modulator, right? And basically we use a phase modulator here to chirp. So this carrier wave here, we actually make we chirp. So we first chirp it, and then we make pulses out of it. So now in this pulse, basically it's chirped. Okay, and how to chirp this? A simple way is just to send some microwave tone here. So if you have some cosine omega n t, right? So omega m is some microwave frequency. Right, so this could also have some amplitude here. I don't know what to call it, like delta or something. Right, so then, so basically here, from the laser, I have e to the I omega naught t, just a carrier. Then I do phase modulation. So after the phase modulation, I have omega naught t, and now the phase is modulated according to this electrical signal. So I have a phase here additional. Okay, and then I do intensity modulation. So here I have now the A of t. So I have some A naught e to the minus t square or t naught square. Right, so now you can see that, so this looks like a chirped pulse, right? Where this is giving me the chirping coefficient. This is just the carrier, this is the intensity or the amplitude. And then the phase here, right? So cosine omega mt for small values of t, right? So if this frequency is low enough, right? So cosine, would vary something like this, right? And this is the sort of the quarter period. So if my pulse width is small compared to 1 over omega m, right? So basically T naught is much smaller than 1 over omega m. Then only this front portion is, you can see, contributing to the phase across the pulse, right? So for these small values of T or omega mt, I can approximate the cos as, so cosine x as 1 minus x square by 2 for small values of x, right? So in that case, you can see here now the phase. So I have a quadratic phase just like chirp, right? So this, and then, this is just a constant phase 1, so that doesn't change anything. And then I have this quadratic phase here. And of course, I have delta m also. Right? So compare this with the chirp pulse. Right? So basically this C parameter I can control with the values of omega m and delta m, right? The amplitude and the frequency of this microwave to the phase modulator. Right? So so this is one easy way to, and I can impart whatever, I can, if I change this phase by pi here electrically, then I can put the opposite sign of the chirp. Okay, so basically by by knowing this broadening, we derive these analytical results by how much the pulse broadens, right? Depending on the initial chirp and the fiber GVD parameters, etc. So we can calculate what is the optimum chirp, that is, what is the optimum input chirp that leads to the smallest pulse width at the receiver and hence the maximum beta rate. And then we can impart, you can choose delta m and omega m appropriately for that to impart the. Okay, so of course this technique only again works with coherent sources, but nowadays we mostly all the long haul links especially use coherent sources. Okay, so the speed chirping is another technique. So you just need a microwave source and a phase modulator. Okay, so these are sort of the four main dispersion compensation techniques that are used to compensate for chromatic dispersion, right? Two optical techniques and two electrical techniques. There's a question: electrical specifications valid for free space visible light communications also? I don't know what that question means. I mean, for free space optical communication, basically instead of the fiber, you have free space, right? So of course, in free space, there are other considerations that you have to consider. There's no dispersion, right? Because free space is just air, so right, it's almost like vacuum. So the dispersion is negligible, right, to say the least. But you have other factors to consider, like turbulence, and for example, you have adverse weather conditions like fog or rain or something, then that leads to scattering and attenuation and what is known as fading for the signal. So free space optical communications is an up and coming field, right? It's not. I mean, this fiber optic communication is well established, and now the whole modern internet is based on that. Free space optical communication is just sort of upcoming, and people are looking at it for different applications. But yeah, those have different considerations. Like, for example, dispersion is not important, but some other effects are important. There's a whole another course on that called optical wireless communications. It might actually also be offered this semester. So I don't know if any of you are doing that. That course deals with those. And then what device is used for phase modulation of the laser? So these are electro-optic modulators, both intensity phase, and you can even have more complicated types of like IQ modulators, etc., that you use for more advanced modulation techniques. All of them are based on this lithium niobate technology, right? So basically the idea is, so lithium niobate is a material whose refractive index depends on the voltage that is applied. So if you apply some voltage across the material, its refractive index changes. Right, so if you have some optical wave passing through, then you know that the propagation constant depends on the refractive index. So if you change the refractive index, then the phase shift acquired through this material will change. Right, so you can straight away see how I can make a phase modulator. Right, I just have like some length of this device here, lithium niobate, and basically I apply this voltage, it changes the refractive index, it changes the phase. Right? So the phase modulator is actually the simplest device you can make out of such a material. Right? So a lithium niobate is known as an electro-optic material, which has this property of the refractive index being proportional to the electric field or voltage applied across it. In other words, it's also what is known as a second-order nonlinear material. So there are other kinds of materials which also satisfy these properties, but lithium niobate is the most popular one, which is used for all these devices. and they can work at very high speeds, up to 100 gigahertz or more. Yeah, so that's the simplest way you can get a phase modulator. If you make some interferometer, right, you split the incoming light into two paths, right, and make some Mach-Zehnder interferometer, and then on one of the arms you modify the phase. Then you can see here that on one of the arms the phase is modified, the other arm is not, and then when they interfere back again, this phase change will be translated to change in the amplitude or intensity. So that's how you make intensity modulators. And as I said, you can make more complicated things, but the basic idea is just this: the refractive index is dependent on the voltage. Question is, can we modulate current for non-coherent laser source also? Yes, you can. So you can use what are known as laser diodes. Okay, so they are sort of just some p-n junction device which sort of so it's intermediate between LED and a fully stabilized laser. Right, so they have broad bandwidths, like a few nanometer bandwidth, so typically like 1 to 10 nanometer bandwidth. And so yeah, you can also you can current modulate laser, you can also current modulate LEDs, right? So yeah, you can, so by changing the current on and off, the optical power will turn on. Right, so with incoherent sources, you can use the simplest on-off keying or intensity modulation, but you cannot use coherent modulation techniques like which encode information in the phase or frequency, right? Because for incoherent sources, phase and frequency is not well defined, right? It's randomly jumping out of the phase. So, but the intensity or power you can still use. So, yeah, so that's what's done. Another question is, can we use Fabry-Perot interferometer for what?
Sir, like you have used a lithium niobate Mach-Zehnder interferometer. Can this interferometer Fabry-Perot will also work for phase shifting?
For phase shifting, I mean, you need something that. So remember, you're starting with an electrical signal, right? I mean, I don't know what you're saying. You're saying Fabry-Perot interferometer with lithium niobate? Or?
Not with lithium niobate. A simple two parallel plate based Fabry-Perot interferometer.
That just has some transmission characteristics, static, right?
Yes.
I want to transfer my electrical information.
Yes, sir.
So how do you do that?
So just to see the constructive and destructive interference pattern, can we use using this interferometer?
Yeah, I guess I don't know. You're asking something completely unrelated, but yeah, I mean, interferometers are that, right? Like,
Okay, sir. Thank you, sir.
Okay, so before we end today, I just want to briefly also discuss how to compensate for polarization mode dispersion, right? So recall we had also briefly discussed this other effect, which is polarization mode dispersion, which is not as usually important as chromatic dispersion, but for very long haul length links can still become important, especially if you want to go to very high data rates. So let's just briefly discuss the techniques for polarization mode compensation also. Okay, so one brute force way to sort of just eliminate PMD totally is to use what are known as polarization maintaining fibers. So recall this PMD was coming from the fact that basically our fiber core is circular and it doesn't remain perfectly circular all along the length of the link, right? There are some stresses along the path and also some tiny manufacturing defects. So there are some small ellipticities introduced in random directions at random points, which leads to these two modes traveling now at different speeds at randomly in different positions along the fiber, leading to some net broadening due to this diffusive effect. Right. So basically, if you can use a fiber which just gets rid of that effect, right, then you can just eliminate PMD totally. So that is one brute force solution, right? So you use so they have now core which is not circular, right? So for example, you have a core which looks oval. So now, of course, the horizontally polarized and the vertically polarized modes will not have the same propagation constant. They'll be different, right? So basically, by design, we are introducing a very high birefringence in the fiber, right? So the problem with the conventional fiber is that there is no birefringence ideally, but there are some tiny variations happening in random directions which introduce birefringence in the random directions, very small, but still randomly varying birefringence along the length, right? But now here we deliberately introduce a very large birefringence, right? And we also know the direction in which the birefringence is, right? So we know the fast and slow axis. And so here we deliberately introduced a birefringence delta n between the effective indices of the x and y polarized modes, which is quite big, right? So recall that in the standard single mode fiber, these randomly the random stresses were introducing birefringences about 10 to the minus 7, right? Here we deliberately make this like something like 10 to the minus 4 or 10 to the minus 3, right? So very big. So now we know these two modes are now not degenerate, right? And now basically any small variations. So now you can imagine this is now highly elliptical. So any small variations, right, either compression or elongation in this direction won't change this too much. At least not enough that one polarization mixes to the other polarization, right? So these random distortions will now change each of these values by, let's say, 10 to the minus 7. That's still much smaller than the difference between these two. Okay, so I know all along the length that my two main orthogonal polarization directions are maintained, right? And so, for example, if I launch this horizontal polarization, it will remain horizontal, right? There will be no mixing with the other polarization. So your polarization will be maintained, polarization maintaining fiber, right? And so there is no question of PMD or anything, right? There's only one polarization which is traveling. So there are different types of polarization maintaining fibers which have like more fancy types of core. So here you have multiple cores. You have like more fancy designs like this with multi cores. Okay, so this is like called oval core. This is called panda because it looks like a panda. You can see. This is like bow tie. Right, so you can make these fancy polarization maintaining fibers, and then you don't have to worry about PMD at all. But of course, you can see that, I mean, these are very complicated, right? So typically they'll have much higher loss than single mode fibers. Also, their chromatic dispersion will be worse than single mode fibers, right? Although you've now eliminated PMD, but each of them will have their own chromatic dispersion, Right now, because of these complicated structures, which will be even maybe worse. Okay. So polarizing material fibers, this is not a practical solution. Also, you need to replace all your like standard fibers along the link with polarizing material, right? Which is just not practical, right? So under very some special circumstances, these are used, but not like for general long haul optical networks. You can't replace everything with polarizing material fiber. Okay. So then, what you do there is that. So again, you can use either an optical technique or electrical technique. In optical technique, what is done is, so after your fiber link at the receiver, you have what is known as a polarization controller. Okay. So basically, so if you launch some polarization here, we saw that due to this random birefringence, now the polarization arriving at the receiver is some random, like some elliptical, some random polarization, right? And also the pulse has broadened, and each of these component or like the within the pulse, different time delays have different polarizations, right? Because of this different speeds. So use a polarization controller. Basically, what you can do is change the ellipticity of this input. So basically, you can give different phase difference to the different polarization components, and then you send this through what is known as a polarization beam splitter. Okay, so you now sort of split your horizontal and vertical components, and then you have a time delay between them. Okay, and then you recombine at another polarization. Okay, and then basically this is your final signal that you are sending to your photodetector, right? So basically by playing with the this polarization controller setting and this time delay, right? You adaptively control these two such that basically you compensate for the delays of the different polarizations and you bring them back together. Okay. So this is like an optical technique, but this needs to be updated real time, both the setting of this polarization controller and the delay, to take care of like the sort of different stresses randomly happening here in the file. Okay, so this is an optical technique. And the electrical technique is like once you detect on your photoreceiver, you're getting some electrical signal again, right? And then you try to use again some digital signal processing technique. So we try to send this through some general filter. So you now have a current versus time or voltage versus time, and basically you send it through some tapped delay line. Okay, and then so each of these has some weights. So this is your incoming signal. You add all of these up. Okay. So basically your this filter response here, so your output can be written something like summation over some m taps. Right. So it's like some tap delay line, right? So delay tau, 2 tau, 3 tau, and you multiply each of them by some weights, and then you try to optimize these parameters, these coefficients, and the number of taps, such that after this filter, basically, your pulse is sort of. There's a question: what is a PBS? So it's a polarizing beam splitter, right? So basically, it splits the horizontal and vertical polarizations, the two orthogonal polarizations, into two different paths. So if you have some incoming polarization, which is generally some elliptical polarization, right, then you can write it as a superposition of H and V. right, with some phase difference. So the components will be split. Right. So for example, if the input beam here is horizontally polarized, all of it will come out here. If it's vertically, all of it will come out here. If it's some other, if it's circular, for example, 50-50 will come out. So it just splits the two of them. Okay, so yeah, this is an electrical technique here to compensate PMD. Yeah, so as I said, PMD typically is a lower order effect than chromatic dispersion. So only for very long links like hundreds of kilometers and at data rates approaching 100 gigabit per second do people start worrying about compensating for PMD after they've compensated for chromatic dispersion.